Dear students, welcome to today's lecture, in which I am going to continue the topic which I have started in the previous lecture, that is cross section of a nuclear reaction. Let us have a quick recap on the previous lecture, in which I have thrown some light on the sources of nuclear energy, and I have tried to refresh your knowledge on the mathematical expressions of Q value of a nuclear reaction. And if you remember, I have written mathematical expressions for nuclear Q value, which consider masses of the nuclei, and atomic Q value, which considers masses of atoms. And because practically it is not possible to measure the nuclear mass, so normally we go for the atomic masses. And I have suggested you to download any app to get the basic properties of the nucleus. For example, you can download International Atomic Energy Agency IAEA Vienna. It is located in Vienna. So, if you download that app, by entering the values of atomic number and mass number or element symbol, you can get almost all information available till now. What are the energy levels of the nucleus, what are their properties, angular momentum, transitions, level schemes. So, almost all properties related to the nucleus you can get from this app, and that will make your job easy while doing the calculations. No need to go here and there. So, in the assignments there will be a few problems which require the use of an app. I am sure you will enjoy this kind of arrangement while solving the numericals. Anyway, so the difference of atomic nuclei, the atomic Q value and the nuclear Q value, how they are related, and under what circumstances binding energy correction can be neglected and cannot be neglected, that I have discussed by taking the help of a positron decay as an example. Okay. Electron with negative charge, ideally we should use the word negatron, but normally we use the word electron, and the impression in our mind is this is a particle which has a negative charge. Okay. But ideally we should use the word negatron, but anyway it is going on in our daily lives, one can use it without any issue. But the particle with positive charge, that is positron, electron with a positive charge which is positron, if it is involved in the decay, then the calculation of Q value requires some special attention, and I strongly suggest you to write down expressions for Q value considering beta minus decay, beta plus decay, electron capture. So, these three processes requires a careful representation in terms of Q value, and that makes the concept also easy for you. Alright, and after that I have discussed the basic concept of cross section of a nuclear reaction. As I said, like in quantum mechanics, it is the wave function which plays important role to understand the subject. Similarly, in this course nuclear astrophysics, there were two objectives, as I said in the initial slide, very first lecture, and I keep on saying in several lectures whenever there is a context. Okay. It is the synthesis of new elements because of the nuclear reaction. That is one of the goals, how to understand the nucleosynthesis. Number two, energy produced from stars. These two are the, we can categorize these two as the major objectives of this course, because they will help us in understanding the evolution of universe, synthesis of elements in the universe, evolution of a evolution of a star from its birth to death stage. All right. And I have explained the cross section as the ratio of, in the numerator you have number of interactions per unit time, and in the denominator you have number of incident particles per unit area per unit time, and number of target nuclei within the beam. So, what does it mean when I say target and beam? In stars, when nuclear reactions are happening, there is no difference between target and projectile, because both are moving in the stellar plasma. So, one has to go for center of mass system for comparing the results obtained in the laboratory. but in the laboratory you cannot have a nuclear reactions that are happening exactly the way reactions are happening within the stars. So, you have to consider a particle accelerator. You might have heard Van de Graaff generator, pelletron, synchrotron, cyclotron, which I will explain in due course. So, when particle beam is generated from the accelerator, it interacts with the target material, and the interaction between the incident particle and the target nucleus is the nuclear reaction of our interest. And how to get an idea of the probability of a nuclear reaction to take place. To study any property of the nuclear reaction, the fundamental parameter which is of interest is cross section, whose units are centimeter square. You can use bar, millibar, microbar, nanobar, depending on the combination of the target and projectile in Earth's laboratory. So, how to mathematically express the quantity reaction cross section that I have discussed in the previous lecture. In today's lecture, I am going to take the discussion forward. The Q value is nothing but an energy produced in a nuclear reaction. It could be negative or positive. If the Q value is negative, you have to supply the energy to the projectile so that reaction can be initiated. If it is positive, then energy is released in the form of some particles, kinetic energies of the reaction products. But here we are not interested to study the mechanism of the nuclear reaction. The main interest is how this nuclear reaction helps us to understand the synthesis of elements in the universe and energy produced in stars. So, we are shifting the focus from Q value to another quantity. What is that? In the stellar plasma, how many number of reactions take place per unit time and per unit volume? I repeat, number of reactions taking place per unit time per unit volume, which we call as reaction rate, which this is the fundamental quantity in nuclear astrophysics. And this reaction rate of nuclear reactions, that is number of reactions are happening within unit time and per unit volume, depends on two factors. Number one, cross section of the nuclear reaction, that means the probability with which reaction is happening. Number two, the velocity distribution of the particles. See, in stellar plasma, particles are moving in different directions, and when there is a high temperature which is causing the thermal motion of the particles, and this thermal motion is giving the kinetic energy to the particles, and when they collide with each other, there is a probability for the nuclear reaction to take place. And we want to understand the energy produced from a star within which all these reactions are taking place. So, it is quite natural to consider this quantity, that is reaction rate, number of reactions taking place per unit volume per unit time, as one of the most important quantities to be calculated or to be measured in this course of nuclear astrophysics. And it depends on two quantities. Number one, cross section of the nuclear reaction and the velocity distribution of the particles, because at a fixed temperature, the velocities of all particles is not same. The velocities of all particles, they are not same. There is a distribution, and in today's lecture I am going to give a few important mathematical expressions for this velocity distribution and the reaction rate. So, unlike previous lectures where most of the things are kind of theory, in today's lecture it is purely mathematical expressions. I hope you will be able to enjoy. Okay. So, let us see how to write down the expression for nuclear reaction rate. Okay. And consider a reaction, say 1 plus 2 giving rise to 3 plus 4. Okay. This kind of reaction is happening within the stellar plasma, just assume. And in Earth's laboratory, what we are trying to do, we are taking this 1 as the projectile, 2 as the target nucleus, and these 3 and 4 they are reaction products. It could be anything. Number 4 could be proton, alpha, neutron and gamma. Number 3 could be any other nucleus. Okay? And if it is scattering, then 1 can be equal to 3, 2 can be equal to 4. Okay? And sigma, that is cross section of the nuclear reaction, it depends on the energy of the particles. It of course depends on the energy of the particles. So, I can write in terms of velocity, And in the previous lecture, I have written expression for cross section of a nuclear reaction. In the numerator, I have written number of interactions per unit time. In the denominator, I have written number of incident particles per unit time per unit area and number of target nuclei within the beam, particle beam. And if you would see the units, all those things will cancel except area, that is centimeter square, which is the unit of cross section. Keeping that in mind, let me write down something here. Okay? Rate of a nuclear reaction. Rate of a nuclear reaction, that is number of reactions per unit volume and per unit time. So, number of reactions, say NR divided by per unit time per unit volume. This is a reaction rate, right? This is equal to cross section into number of target nuclei within the beam, okay, and number of incident particles, that is particle beam NB per unit volume. The area of the beam is A and per unit time, all right. And this I can write as sigma into NT by V NB divided by area into time, and this I can separate as sigma into NT target nuclei divided by unit volume, and here I can write down velocity, and NB, that means number of particles within the beam per unit volume. Now, here let me introduce a quantity, that is current density. This is of importance when you do experiment using particle accelerator. Okay. Current density, that is number of particles per unit area per unit time, is given by JB is equal to NB, that means number of particles within the beam, and time into area. This in terms of velocity I can also write like this, V into NB divided by capital V. Okay. And this is how one can write a basic expression for the reaction rate. Now, let me use a symbol, okay, small r 1 2. What does it mean? 1 is a projectile, 2 is a target, or vice versa, it does not matter. So, this reaction rate r 1 2, okay, assume that 1 and 2 they have the rest mass, okay, unlike gamma ray. So, this r 1 2 can be written as number of reactions divided by time into volume. Okay. This is r 1 2, and this can be written as n 1 n 2 velocity into sigma, which is function of velocity, where n 1 is equal to, for example, if this is a target, okay, n t divided by V, and where this n 2 is nothing but number of projectiles, okay, n b by V. They are the number densities, of the interacting particles per volume, okay, in units of particles per unit volume. Now, at thermodynamic equilibrium, the velocity is not constant, but as I said earlier, the distribution is there in the relative velocities described by a probability function p as a function of v. Okay. And in this case, p as a function of v dv is the probability that the relative velocity of the interacting nuclei is in the range of v and v plus dv. So, how it can be defined? Starting from 0 to infinity, p as a function of v dv is equal to 1. Now, let us generalize the reaction rate for a distribution of relative velocities by writing R12 is equal to, I can write N1, N2, 0 to infinity. Just I am rewriting this equation. Okay. Velocity into probability for velocity distribution and sigma as a function of energy, that is velocity, and dV. So, this I can write like N1, N2, sigma V12, where this is called as reaction rate per particle pair, and this N1 and N2 is the total number density of pairs. Remember, they are non-identical. For identical, you need to rewrite this expression, non-identical nuclei 1 and 2. See, for identical case, how do you write down this expression? For identical particles, for identical case, we can write like the total number density of the pairs is given by N1 into N1 minus 1 divided by 2, and as N1 goes large, we can write like N1 square divided by 2, and this leads to reaction rate for identical case as N1 N2 sigma V12 divided by 1 plus delta 1 2, where this delta 1 is 1 2 is called as Kronecker symbol. Kronecker symbol. The number of reactions per unit time per unit volume. This is important because this reaction rates decides the abundance evolution of elements in the universe. So, that is the reason I am discussing the mathematical expressions for the reaction rates when two particles or two nucleides of same nature or different nature, they undergo nuclear reaction. Let us continue the discussion on this topic. Okay. So, let me go to the next slide. So, here in the previous slide I have written the expression for reaction rate for non-identical and for identical particles. Okay. So, number of reactions per unit time per unit volume is nothing but the product of number of particle pairs and the reaction rate per particle pair. Please remember this, sigma V12 is reaction rate per pair. Okay. And this quantity contains the information related to nuclear physics. Normally in practice, we multiply this with Avogadro number, sigma V with Na, and this is Avogadro number. Okay. And units of this reaction rate is given as centimeter cube per mole per second instead of sigma V, which is tabulated and we can see in the literature also. Okay. Now, you know that in the stellar plasma, the kinetic energy of nuclei is available from thermal motion, as I said already. Okay. Therefore, these reactions are called as thermonuclear reactions. Thermonuclear reactions. And where from this thermal motion has come into picture? When some initial stuff is available, say starting with the hydrogen, because of the gravitational attraction, all the protons they come together and the gravitational attraction makes the condensation of this hydrogen matter, and after certain stage this gravitational contraction leads to the production of thermal pressure, and this thermal pressure leads to the occurrence of reactions between the nucleides like particles, okay, like protons. Now, the energy liberated from these nuclear reactions will try to stabilize the star. Because the reactions are initiated by the thermal motion, we call these reactions as thermonuclear reactions. Okay. So, let us continue the discussion of these thermonuclear reactions. Fine. So, we have written the expression for reaction rate, and in most cases the velocities of the nuclei can be described by Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution, and the probability for the occurrence of a nuclear reaction depends on the sigma depends on the relative velocity, as I already discussed. Okay? And we can write now the probability expression P of V dV, taking the case of Maxwell-Boltzmann distribution, reduced mass of first and second reaction initiators, okay, and 2 pi k T to the power of 3 by 2 e to the power of minus m12 velocity square. This expression you know very well if you know the basics of statistical mechanics. Otherwise, you can go through the details of Maxwell-Boltzmann distribution, okay, Fermi-Dirac distribution and Bose-Einstein distribution. And because in this case we are dealing with the fermions, here the particles though may not look like they are fermions. It is an interesting question that I ask you people, why it makes sense to consider the distribution as per the Maxwell-Boltzmann distribution, but not Fermi-Dirac distribution though they are fermions. I repeat the question, why Fermi-Dirac distribution is not taken here, and how Maxwell-Boltzmann distribution is considered when the motion of these positive ions in the star is taking place under high temperature. Okay? So, this expression for Maxwell-Boltzmann distribution is well known to you, and this gives the probability that the relative velocity has a value between V and V plus dV, and the value of k in terms Kelvin. I strongly suggest you to remember, okay, 10 to the power of minus 5 electron volt per Kelvin. You can express Boltzmann constant in any units, of course, but here in this particular course per Kelvin unit of Boltzmann constant is highly preferred, because you are dealing the temperatures in kelvins, 10 to the power of 6 kelvins, 7, 8, 9 kelvins, like that. Okay. So, after this expression of probability distribution in velocities, let me continue the writing the expression for reaction rate. Before that, please remember here m12 is equal to reduced mass m1 m2 by m1 plus m2, and we know that energy is m12 v square by 2. Okay? And if you take the differentiation with respect to velocity, you will get velocity into m12. Now, let me rewrite the expression for probability P as a V function of and dV. I can always convert in terms of energy, probability as a function of energy, and this gives rise to m12 2 pi k T to the power of 3 by 2 e to the power of minus e by k T 4 pi 2 e by m12 d e by m12, and here I can write down m12 divided by 2 e, and if you simplify this equation, it comes out to be like k T to the power of 3 by 2 square root of e to the power of minus e by k T d e. And what is the maximum value of velocity at which the distribution has a maximum? V t is equal to 2 k T divided by m12, and corresponding to this the energy is k into T. So, please remember this expression carefully, and this will be very useful, and the energy distribution has a maximum at E t is equal to k T by 2. And now, the reaction rate per particle pair sigma v 1 2 can be written as 0 to infinity, okay, velocity and probability distribution in terms of velocity sigma into v dv, and it is easy to write down in terms of energy, that is v sigma is a function of energy, probability as a function of energy already have written dE, and this can be written as 8 by pi m 1 2 to the power of 1 by 2 and 1 by k T to the power of 3 by 2 0 to infinity e sigma into e e to the power of minus E by kT dE. Okay? And please remember the units are centimeter cube per mole per second. Now, where the center of mass energy, if you take, is in MeV. In this particular case, this units of E is in MeV, and T, if I write in terms of, okay, let me write down the next slide this expression of reaction rate by converting into another form. Okay. At a given temperature, the most commonly used expression for the reaction rate is multiplying with the Avogadro number. Okay. And numerically I can write this as 3.8 into 10 to the power of 10 T9, where T9 is nothing but 10 to the power of 9 kelvins. For example, T9 is say 1, that means 10 to the power of 9 kelvins. T9 is equal to 2, that means 2 into 10 to the power of 9 kelvins. Okay. So, T9 to the power of 3 by 2, all right, and this gives me M1 plus M2 by M1 M2 integration from 0 to infinity E into sigma as a function of energy. This expression you can easily derive yourself, and I strongly suggest you to derive yourself. Okay? And the units is centimeter cube mole per second. Okay? And here it is in MeV. Okay? And T9 is in gigakelvin. Okay? Gigakelvin, and this M values, they are in atomic units. Okay? And cross section is in bar, sigma is in bar. So, please take care of these units and numbers, and accordingly try to derive this relation from the previous expression. Okay? So, clearly the reaction rate depends on the cross section, which is different for each nuclear reaction. So, in this lecture what I have tried to show you how to mathematically express the reaction rate occurring in the plasma. Though earlier you were more confident of depending on the Q value to understand the energy released from the stars, but it is not like that, because so many particles from different stages of the star, they are undergoing reactions, and the fundamental quantity of interest is number of reactions taking place per unit time per unit volume. So, that 3-dimensional case one has to consider. Okay? Though Q value of the nuclear reaction helps us in designing some experiment. Okay? So, in today's lecture, please try to derive the expression for reaction rate per particle pair after multiplying with the Avogadro number. These formulae, which involve the Maxwell-Boltzmann distribution, probability distribution, product of probability distribution and the sigma, they are going to play a very important role to understand the physics aspect of the star's evolution. Thank you so much for your attention. In the next lecture, I will discuss more mathematical formulae related to the charged particle reactions and reactions induced by photons. Okay? Thank you so much.